Good morning. Today we're going to be looking at what it takes to make a class comparable so we can do some really fun things like sorting information or ranking objects, because unfortunately objects by themselves just can't do that on their own. So this is Cody Hendrickson. We're going to go ahead and take a look at that. So we want to compare an object, and in Java, an object itself is something that exists on its own, so it has its own structure, but we can't use relational operators. The greater than, less than symbols just don't work with object types inside Java. So we have to make sure we actually create the functionality within that, and we do that by using the comparable interface. And all we have to do the comparable interface is we have to add the keyword implements to the class header, and then comparable of whatever type of thing we're making to that, and then go from there. Now we already have a structure of those strings. We'll demo if that works, and then custom implementation, and then why we're going to do this. And the big reason is so we can sort things. So the comparable interface, this is what allows for things to be sorted. AKA, you want to be able to compare this thing to this thing. In the case of cards, for example, I have a deck of cards. I want to be able to compare this card to this card. Now, with a card, we have the idea that we have a 5 of diamonds versus a 7 of diamonds. And how do we relate them? What makes one card better than another? They have the same height. They have the same weight. They have the same basic back color. And like, oh, they have a 5 and a 7. So what makes this one less than this one? Oh, or this one less than this one? Depends on how we actually look at it. And that's where we use the comparable structure. And because they're objects, we have to use a method for this. Because again, objects work with methods. It's the whole idea of object-oriented programming. The Java language uses the standardization with an interface structure. It's one of the easiest ways of doing polymorphism or many types or many forms that we can do so we can have lots of different things, have some functionality across the board. And the comparable interface is the big interface we'll use most often when we're talking about sorting information. The information you have to do will work for anything. Now, the really cool and amazing thing is because it's a comparable type, I can make anything work within that because it's comparable. So any comparable object can use the same sorting structure. So I can sort cars, I can sort bananas, I can sort cards, I can sort remotes, I can sort anything. It's a really amazing thing that works for that. Now, the only thing we have to do is we have to, in order to implement the comparable interface, is we have to write the code to support the public int compareTo method of whatever type we're working in compared. And so we'll take a look at how to do that and go from there. Now, in AP, we have to use comparable already with the string structure. The AP course descriptions talks about using the .compareTo method on strings and how it works. Now, this is an English lexicographic structure, how the dictionary would sort it. And so all capital letters have a lower ASCII or Unicode value. And so we have ASCII values are lower than everything else because it's part of the basic Latin set of Unicode. Capital A to Z is lower than lowercase a to Z. Capital is smaller than lower. I know, but it's the way that we actually structured Unicode. You can go take a look at the structures that go along with that. It's its own big, huge thing, but hey, no big deal. Now, also on the string comparison, it's language dependent. Not every single language is the same contiguous range of values. This is especially noted in, we saw in class with the Cherokee language, where the uppercase and some of the lowercase are in one chunk of Unicode, and the rest of the lowercase are a completely different chunk of Unicode values. Yeah. And then if we look at different Latin sets, it goes upper, lower, upper, lower, upper, lower, upper, lower, instead of all uppercase and all lowercase like we see in English. So using that structure of comparison is going to give some different values when we're looking at languages that are not English. But it's a great thing to look at and see you can actually do some cool information sorting. And then, well, yes, we have emoji. The cute little symbols you use all the time on your phone are also strings in Java. And so when you're comparing them, you get some interesting values with that. And we'll look at an example of that as well. The basic string compareTo example is what we see right here. We have capital A.compareTo lowercase a gives us a negative value. Lowercase a.compareTo a returns a 0. And lowercase z.compareTo a gives me a positive value because z comes after a on that structure. So we're looking at what we have over on the left hand, the caller, and how it compares to what's inside the parameter. So call versus parameter is where we see that reference happening inside strings. Now here we see the actual example of the code, both the execution and the actual code that goes along with it inside this example code right here. So my compare strings method, and I have a compare to z and what it evaluates to, and then at, za, race car. For non-English letters, we have the ex and grav compared to the lowercase ex and grav for that compareTo. And then using a completely different language, using the Japanese character sets of hiragana and katakana, we have the hiragana u compared to the katakana u and see what that result is. And so we'll take a look at that. And then we have emoji. Now, if we have the A to Z, we have the value, it's negative 25. A compared to A, negative 32, because capital A comes before lowercase a, so it's a negative number. We have we have z compared to lowercase a gives us a negative 7 because big Z is 7 before lowercase a. Oh, okay. Then we have race and race car. Race is negative 3 race car. Oh, yeah, because that was extra letters. Those 3 extra letters means there's 3 more spots asked to compare, and that's where we see that value on that. Not very helpful, but it's there. Then we look at our non-English characters. So EX and grav compared to EX and grav lowercase, also negative 32 apart. However, when we look at the Unicode values that are compared to using the Japanese hiragana and katakana alphabets, we have U compared to U is a negative 96 apart, which is a very big difference when we're talking about. But this is something that's standardized across the different languages for most of the cases that we're looking at that. And then we have emoji. Soccer ball, rice cake, dumpling, dot compared to surfer, picture, person, is negative 45,439. Yeah. We don't want to actually sort letters versus this, but that's the idea that we can do comparison on that, and that dot compare to method works for every single string. The actual results we get back are dependent on that. And so this is something we have to actually do some evaluation on and how we're going to actually do some sorting of strings lexicographically, because the soccer ball is so far before that, it's like, oh, okay, how's that going to compare? It's going to be after everything in our English language, but where is it in relationship to the other different parts of the string library inside Unicode? And that's a big question. So that's a great thing to take a look at, and you can do some really cool examples with that inside projects. Now, in order to make this happen, we have to have a comparable of type. Now, the type is whatever we're making that comparison of, and so this is what we're going to be doing inside our interface. We have to do the comparable of type, and this interface is what we allow us to make that comparison on. Again, the only method we have to actually write for that interface is compareTo. And remember that an interface is, remember that the keyword implements, when we write that in the class header, is a promise to fill out all of the code that belongs to the interface that's specified after the interface the implements keyword. And so this is something you actually want to design in advance. Now, we have the famous phrase, weeks of code can save hours of planning. If you simply just throw the code on the screen, it's going to cause some problems. So you want to actually plan this out before you actually try and write the code, because when you actually build the structure of a comparison, you want to make sure it makes sense logically before you try and do it. Another reason you have to do this is it has to be both transitive and clear. You have to be able to make sure that it works. If A is less than B and B is less than C, then A is also less than C. It has to be a transitive approach. You can't just simply just throw stuff out there. It has to work across this. The next thing we have to keep in mind is that there has to be a clear structure. It has to be able to make sense. Like, oh, we have right here, we have the 7 of diamonds versus the 7 of spades. Which one is going to be less or greater than that, or are they equal? We have to make sure it's easy to understand, so when I compare these, the value that returns makes sense. It shouldn't be some wishy mess. It needs to be something we can actually understand and be able to implement. So we have right here our ZombieHead UML. We've used our ZombieHeads in a couple other projects, and you can take a look at those in other videos. But we have in our UML diagram right here, we have our ZombieHead class. It has a string that's name, an int that's its grossness level, a constructor that has a random grossness level attached to it, and a constructor that has a name and construct. It has a constructor that has a random grossness level attached to it and a default name, as well as a constructor takes a specified name and a specified grossness level, and of course the getters and setters. Now, that's not the most amazing class, but that's what we're going to be starting off to so we can use and actually sort this. So let's take a look at what we're doing. When we start with this originally, we had a dot equals method for our ZombieHead methods. We can say if this ZombieHead is the same as this ZombieHead and talk about if they're the same thing when we're looking at looking through a list. The problem with that though is when we're seeing if this ZombieHead and this ZombieHead are the exact same thing, it's like, oh, we'll make it kind of squishy. And we said if its grossness level is within 20, if that's okay. It was great for doing that quick, easy example of that. But by throwing that code up there, not doing actual some planning, we run into some problems because when we try and sort things, if there's a range of 20 values that could possibly be considered the same, it doesn't going to look well sorted. So we have to actually fix that. So we also have to write our compareTo method. And when we write the compareTo method, we have to look at the actual object itself. And when we look at the object, what we're looking at as a whole is what makes that object what it is. And so we look at a ZombieHead. So when I'm looking at a ZombieHead, I have to actually look at the data members of the ZombieHead itself so I can keep track of what I'm going to do to sort these cute little ZombieHeads in their list. And the way we want to do that is we want to look at either the names or the grossness level. Now, the problem with names for ZombieHeads is those names can be very distinct because each human being has its own name. And if you're trying to rank names, I'm like, is this name better or worse than the other name? It's going to be kind of hard because you've got George and you've got Sergio, and which one of those is better? And that's really more of a personal preference. So instead of using names on that comparison, they're very distinct, they're hard to make that comparison. We're going to look at grossness level. And so do we have this grossness level of this lovely ZombieHead, or do we have this grossness level of this ZombieHead, or do we have this grossness level of this ZombieHead where it's slightly covered up and not quite as gross? I know, it's amazing. So we use that grossness level head to actually take a look at that so we can see how gross those ZombieHeads are. And it means that we are going to have to go ahead and change the squishiness of our equals method. Now I did leave it a little squishy. I'm going to still have it be a not exact match, but now if the difference is less than 2, because it's off by 1, that's squishy enough. I'm okay with that because I want to have some squishiness because squishy ZombieHeads are always cool. Now here we have our updated equals implementation of the ZombieHead's .equals method. And remember, when we're writing our .equals method, the .equals method takes an object as a parameter. It doesn't take a ZombieHead, it takes an object. And so we take that object parameter and we say the match is set to false. If this equals other ZombieHead, if they were talking about the same space and memory, then yes, that's true, we'll return true automatically. Then we have to check to make sure if the other object, we first have to make sure, is it a ZombieHead? Because if it's not a ZombieHead, it's clearly not the exact same thing. And that's where the instance of keyword comes into play. Then we say if ZombieHead other is, then I'm going to cast that other ZombieHead as a ZombieHead. And I'm going to do a math.abs change on that. And if the math.abs of the difference between those two levels is less than 2, then sweet, we're good. We've got a ZombieHead that matches. And that's where we return that match value. Then we have our updated implementation of that, so we can do the compareTo method. Now, in the ZombieHead compareTo method, we want to make sure that we're giving a value that's either going to be a positive value, a 0, or a negative value. Now, the actual numbers we use on this don't really matter, but for the purposes of this, I'm using the most simple and easy and basic way of doing that: 0, 1, and -1. The first thing we have to check first, of course, is it the actual same ZombieHead? So the .equals has to happen first. So if other .equals this, then yes, return 0. We've got the right ZombieHead. Else if the grossness level of this thing is different from the grossness level of the other in a negative fashion, return -1. Otherwise, return 1. So we have a 3-part return statement. We could write that a little bit differently, but this is what we're using for the basic and easy, simple compareTo method. Take a look at some of my other videos so we can talk about other ways of comparing things, especially how we use the debug duck. So we use a little bit different structure for that one. Then we can see the comparison is structure on that when we write our compare zombies method. So I make 3 zombies right here, sample 1, 2, and 3, and I give them associated grossness levels of 213, 300, and 0. And we see what the comparison of sample 2 to sample 1, sample 1 to sample 2, and sample 3 to sample 1. And so sample 1 compared to sample 2 is -1 because sample 1, 213, is less than 300. Okay, negative value. Fantastic. Comes before it. Sample 2 compared to sample 1 gives me a Sample 2 compared to sample 2 gives me a 0 because 300 and 300 are the same. That should definitely be the same. And then sample 2 compared to sample 1 gives me a positive number because 300 is after 213. Oh, good, good, good. And just for giggles, we'll take 3 and 0. So sample 3 compared to sample 1 is -1 because 0 is less than 213. So you have it working properly. So we can see that these are working appropriately as our structure on that. We have our updated ZombieHead UML, so we can take a look at that. So we took to our grossness level and name on that. We added a method for that for the .equals method and .compareTo, and those are both public methods. And so now our updated ZombieHead UML, so if we were to do more project with that, we have a clear API of what we can use to actually talk about our ZombieHead and what it can do. And that's where we're going for that. Now, we can see right here the actual structure of the ZombieHead class. Now, I'm not going over the detailed implementation because we already talked about the .equals and .compareTo methods earlier, but we can see right here that we have the class header right here where it's a public class ZombieHead, implements comparable, and in our angle brackets, ZombieHead, which means that this thing can be compared to any other ZombieHead instance, and it works really well for doing those comparisons. You could also do a comparison on some other type that's more broad scale than ZombieHead. It could be like all zombies, but that'd be something we'd have to take a look at when we talk about more the of inheritance, how those structures are working. But ZombieHead itself works really well. And as you can see, it's just a really simple class. It has a ZombieHead constructor, like a second constructor with an overriding name and a value. And then we have our getters and setters that go automatically, just working regular basic stuff. And then finally, we have our .equals and .compareTo methods. And that's all it takes to make that ZombieHead class structure work. The next thing we have, the amazing power of the comparable interface, is that we now have the ability to use the built-in sorting features that exist inside the Java language. Inside Java arrays class and the collections class, we have sort methods that can already do all of our amazing, really efficient, highly optimized sorts for us using the magic power of an adapted TIM sort. So the pre-optimized TIM sort that works for any object that implements the comparable interface will work inside that with using arrays.sort or collections.sort, and we can pass it an array or a list of any object of type that is comparable. And so the list of the type or the type square bracket array that is passed as a parameter to the associated sort method will then be returned as a sorted value. You can even do more complex and more powerful sorts by using comparators as parameters as well. So you can do, I'm going to make this more powerful sort, but it uses the ability to use those built-in sorts that are really quite powerful and really fast. And you can have that already built in. This also makes it so that you can do the more customized sorts that we do inside like selection sort, insertion sort, merge sort, or quick sort. And you can use those codes like that by using a proper object, using the .compareTo method. And we'll take a look at that in other videos as well. Thanks again and have a great day. Bye.